Alright, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we're going to be talking about calculations involving KB. In the previous lesson we talked about calculations involving Ka, which turned out to be just basically equilibrium calculations from a previous unit in a slightly more focused form. And today will be no different. The only difference, I suppose, is that instead of KB, we're going to be using K, or instead of using Ka, we're going to be using KB. So the biggest differences between Ka and Kb problems is that Kb is not usually given to you, and you usually have to calculate that from the table. Now, if you remember, calculating Kb is done using this equation here. Kb is Kw divided by Ka. Ka you can pull from the table. And because the resulting solutions will be basic in nature, we'll be calculating concentration of OH minus, or we'll be using concentration of OH minus as opposed to using concentration of hydrogen. All right, so let's jump into the first example. So in your textbook, this will be example on page 152. And it asks us the following. What is the pH of a 0.10 molar solution of sodium cyanide? For this problem, we have to decide whether the ion will act as an acid or a base. To do this, we'll have to find the acid or conjugate acid on the table. And from there, we'll have to calculate the Kb. For this example, we'll have our sodium cyanide will dissolve into sodium ions and cyanide ions, and the cyanide ions can react with water, hydrogen cyanide, and OH. What we're going to look for in our table is this. Alright, let's just give myself a little bit more room before we continue. So here's our table of acids and bases and Ka. We're going to look for hydrogen cyanide. Ka of HCN is 4.9. So the Kb of Cn minus will be Kw divided by the 4.9. But Kw is 1.0 times 10 to the negative 14 at root. Carry out this calculation. Alright, so there's our Kb. Now we know what the Kb is equal to. Kb is 2.0 times 10 to the negative 5. Where do we go from here? Now we need our rice table. Write down that we have 0.10 molar. Yes, right? Okay, and because we know that this will fully dissolve, 0.10 molar NaCN will translate to 10 molar Cn. This will become important because when we create our rice table, we're going to use the following reaction. The Cn minus plus water will equilibrium with HCN and table, so it looks a little neater. Alright, now the initial concentration, because our salt fully dissolves, being a sodium-based salt, we can put 0 there. Water doesn't matter because it's a liquid and it's the only liquid in the solution, so it doesn't actually affect our equilibrium calculations. We start off with none of this, which means then our change, this will have to get smaller, this will have to get bigger, and this will have to get bigger. We're going to make the assumption we did in the last set of calculations where this change will basically be the same because the change will be very, very small. So we're going to assume that the change is very small so we can make this column a little easier to work with. And now we just set up our equilibrium calculation. Because if you recall, Kb is really just concentration of the products that divided by the concentration of the reactants. We have our Kb value was 2.0 times 10 to the negative 5. OH minus we don't know, HCN we don't know, and Cn minus we're going to assume is 0.1. Right, carrying out the calculation, 2.0 times 10 to the negative 5 times 0.1 will be 2. This will become x squared, so we square root that, and we get the following. So 1.14, 1.41. 1.41 times 10, and then if I square root the negative 6, the same as dividing. Right, so this is x, which also happens to be the concentration of OH minus, and also happens to be the concentration of HCN. Now the question is asking us for what is the pH, I believe. Let me just check. Yeah, what is the pH? Now what we could do is we could do another equilibrium calculation using the concentration of the acid, but we don't actually need to do that. What we can do instead is use this information and we can calculate pOH. Because if you remember, pH and pOH are related. So if I do this, pOH is negative log of the that. So get a pH of 2.9. Sorry, pOH of 2.9. And from the pOH, we can get the following using our relationship between pOH and pH. 14 minus 2.9. And there's our final answer. So even though the question was giving us a base, because we know that how Ka and Kb are related, it just takes one or two extra calculations to go to what we need to go to. On to the next example. So the next example is on page 153, and it reads as follows. We're given the pOH of a half molar solution of a weak acid, and we're asked to find what is the Kb. So this one's really asking what's the Kb of the conjugate acid. And even though this is in the Kb calculation, this is actually kind of a cleverly disguised acid problem. So what we can do is we can convert the pOH to pH. Then from the pH, we can get the concentration of hydronium. From the concentration of hydronium, we can then solve for Ka and finally Kb. All right, so first thing, we're going to convert the pOH to pH. So pH is going to be 14 minus pOH. So this would be 4. So this would be 3. There's my pH. And then now we can calculate the concentration of hydronium as 10 to the negative 3. There we go. 4.36 times 10 to the negative 4.37. Yeah. All right. Now we have the concentration of hydronium. What are we going to do with this? We are going to create a rice table. So the rice table with that concentration of hydronium, our rice table will look like this. Since we have no information about the weak acid, I will just write down weak acid plus water will create an equilibrium with its conjugate base and hydronium. Okay, we don't care about that because it's the only liquid in the solution. So now we know the concentration of my hydronium is equilibrium concentration. The change would have been a plus x, would have started out as 0. This would have been 0, this would have been a plus x, and this would be the same. This is our unknown, so we'll give that another variable, we'll call that y. We make the same assumption as before, that since x we're going to assume is much less than y, then this here was really just going to be y. Now, we actually know what the original concentration is. I just realized that's 0.5. So this is actually going to be 0.5, which means this. Now I can say the following. Well, now that I have all my equilibrium things filled out, the Ka of this particular acid is 4.37 times 10 to the negative 4 times itself. So I'll just square that, all divided by 0.5. Okay, so it'll be 3.82 times 10 to the negative 7. Okay, but we're asked to find the Kb. So So Kb will then be Kw divided by 1.0 times 10 to the negative 14 divided by then be 0.262, and this will be times 10 to the negative 7 using exponent rules. Just a bit, 2.2 times 10 to the negative. There we go. And there's my Kb. So be mindful that in some of the questions you do, that if it seems you might have to take a roundabout way to calculating Kb or concentration of oxide. If all the information given to you is acid base, you might just work with it as an acid and then convert to the base information later. All right, I think one more example asks us, what is the pH of a saturated solution of calcium fluoride? Calcium fluoride has a KSP. So here we actually have a substance that does not fully dissolve. So calcium fluoride will form calcium to fluorine. This will actually require us to do rice. One for this equilibrium, another rice table for the actual base equilibrium. This will require a lot of room. Right, so our first rice table will be based on this reaction here. There's a little bit of information that we're not given, but we can assume. The CaF2, we can assume this is a solid, so none of this information actually means then that our KSP equation basically just be the concentration of calcium 2 plus times the concentration F minus, but because there's two of them, this will be squared. So we know that at the beginning, that's none of the ions. They will gain. So in our KSP equation, we can following. KSP, concentration of calcium ions, so times the concentration of the fluoride ions, which is 2x, but that'll be squared. Simplifying things a little bit, then we just solve for x. Solving for x will be necessary because we need to know this concentration. The calcium 2 plus won't react with the water. It'll be the F minus. All right, so divide by 4 and then put it. 1.46 times 10 to the negative 10. That, and then we will cube root that. 3.317. Therefore, 2x is going to be 6.74. Right. Now, the F minus, this is going to be the thing that reacts with water. Reason for that is if I look for F minus in our table here, I think F minus is, there's F minus. F minus will react with water. It is the conjugate base of a weak acid. So that's what'll work. This will create HF, and there's our next reaction. Water side we don't care about. Here this is going to be 6.74 times 10 to the negative 4. Change, this will be minus x, this will be plus x, this will be plus x. I should use a different variable because we already used x. We're going to make the assumption that the change is going to be really tiny. Alright, so now this will calculate Kb. So Kb will be concentration of OH minus, minus, and HF, all divided by the concentration of F minus. I actually know what the Kb of F minus is. Yes, I actually do, because Kb is Kw over Ka, and because we were able to find F minus on our table here, we can use that to find the Kb of F minus. So Kb will be 1.0 times 10 to the negative, all divided by the Ka, which was 3.5 times 10 to the Kb of 0.286, 10 to the negative 10. Simplifying this will be 2.86 times 10 to the... There's my Kb. Concentration of OH and F minus is Y squared. F minus is 6.74 times 10 to the negative 4. So we'll have to multiply the two together and then square root it. So square root all that, that'll equal what Y concentration. Okay, we get Y equals 1.397. That's a very small number, even when comparing to the original concentration. Now that we have our concentration of hydroxide, Y was equal to was the concentration of hydroxide, 1.397. We can then calculate the pOH. We'll find the pOH from this using negative log. This is negative log of 1.7. Have it in there, so we'll just go log. So it's negative 6.86, but it's a negative of that, so 6.86 is my pOH. And then the pH we can get using 14 minus pOH. So altogether this is going to be 14 minus 6.86, which is equal to 7.14. I'll check that. 14 minus 6.86, 7.14. There you go. There's our pH. All right. So this problem did require quite a lot of space. Does seem a little difficult at first, but it's really just two different rice tables. All right. Your assignment then for this section is more calculations, basically more of the same. Take your time with it, and if you guys have any questions, you all know how to contact me.